Hello, my name is Cielniak, and I'm an assistant professor at the University of Lincoln. The title of the talk is Soft Food Perception in the Wild. The scope of this work is the application of computer vision techniques for the benefit of the soft food industry, including detection, localization, and quality assessment of soft foods such as strawberries. It is a portfolio of research undertaken by a team from the University of Lincoln and specifically newly established Lincoln Agri-Robotics Center, including my postgraduate students Raymond, Justin, Adrian, and Nikolaus. The main challenge for the horticultural industry is labor. This is due to the fact that the majority of production, which is complex and not easy to automate, still relies on traditional manual operations. The labor availability and cost is a constant challenge due to socio-political pressures such as aging population or migration control, resulting in unsustainable production arrangements. Our team from the University of Lincoln is working on a technological solution addressing that challenge, which we call RASberry, Robotics and Autonomous Systems for Berry Production. This is a funding program consolidating resources from UK, Norway, and industry to develop robotic fleets for monitoring, care, harvest, and logistics in soft fruit production. The core component which drives our agri-robotics technology is a reliable perception system, providing information about crops, plants, and the entire farm environment. For example, a vision system designed for recognizing strawberry fruit can be used for plant health monitoring, yield forecasting, but also for guiding a robotic arm able to pick individual fruit. Development of effective and efficient vision systems for the soft fruit industry is not easy, however, due to numerous challenges. Just to give a visual impression about the challenges faced, here is our agri-robot Thorvald, operating in a real small-sized strawberry farm. Note variable lighting conditions, reflections, occlusions, the non-rigid structure of the strawberry plants, which constantly changes over time, and the relatively small size of the fruit. Another reason I'm showing this footage is to highlight that although a research facility, this is a real, well-maintained, tabletop farm producing yield comparable to other professional berry production sites. The data collected from this farm is the basis for all research presented today, and the robot features a multi-camera system which we use to collect data from multiple seasons and different views. One of the basic functionalities for the fruit perception system is to confirm that the fruit is present at a specific location. The majority of modern detection segmentation systems rely on data-driven convolutional neural networks, which, through the process of learning, determine the important features discriminating the object of interest, which is strawberry in our case, from the background. The state-of-the-art methods include architectures such as faster RCNN, which excels in accuracy, or YELLOW, which favors the speed, and which both demonstrate the excellent performance, providing there is a lot of training data available. We propose an architecture which combines the benefits of these two architectures, and for that purpose we use the input augmentation technique, which in addition to standard color channels uses a biologically inspired color opponency input, which is just straightforward color space mapping, together with an efficient ResNet architecture. We evaluate the proposed architecture on multiple views and real-world data. The output from the system is visible here, where individual strawberries, both ripe and unripe, can be seen. We demonstrate here that combining RGB and color opponency indeed improves the detection results, which are competitive when compared to state-of-the-art, and also demonstrate very efficient inference times, which allows the system to work in real time. The system is also robust to viewpoints, although struggles with unripe strawberries, which have a less prominent opponency signature compared to the ripe berries. In recent years, 3D camera sensors have become affordable and prominent in many robotic systems. These are being used in agriculture, mainly to aid localization of objects in world coordinates. In our own previous work, we have demonstrated that shape information can be used as a discriminant for uniquely shaped crops such as broccoli head. So our investigation here was to evaluate the usability of 3D information and modern sensing technology for the task of segmenting out small reflective objects such as strawberries from the background. To that end, we compared two competing 3D sensing technologies, infrared stereo and time of flight, together with an efficient 3D network architecture. 3D neural networks are typically inefficient due to problematic implementation of convolutions, which are the core operations. We employ an architecture which exploits the organized nature of the 3D data originated from the camera sensors and compare the proposed solution to two baselines, standard 3D network called PointNet++, and also a 2D segmentation standard called SegNet. The proposed system results in more accurate segmentation results and inference times an order of magnitude faster than state-of-the-art PointNet++. We demonstrate that the time-of-flight cameras perform better than stereo in challenging outdoor environments like ours, and while the current 3D systems, and this is mainly due to limitations in sensing, cannot achieve yet the performance of 2D-based solutions in our application, the shape information bears vital discriminative information when the quality of sensing is at a certain level, which we demonstrate in simulation. This provides a useful reference for future development in 3D sensing. So here we've got an example of two different technologies compared, stereo and time-of-flight cameras, together with the simulated results, and we can see the output from the systems indicated in the bottom row and the green color indicating the correct output and other colors indicating disagreements with the ground truth. Another strand of work considers fruit quality monitoring, which is another important aspect of the strawberry production and still relies a lot on human experts. The agronomists look for any potential source of disease or health risks and recommend suitable preventive actions such as spraying or removal of affected berries. To automate this process, we propose to use a vision-based anomaly detection system which identifies unhealthy fruit. Due to a large variation in appearance and type of anomalous berries, standard machine learning techniques, as those presented earlier, are not practical, since the collecting of a sufficient number of examples is costly and time-consuming. To this end, we propose a so-called one-class classifier, which models the distribution of normal, healthy berries, which are easy to annotate in large numbers and indicate which cases deviate from the norm. The proposed system is based on a support vector data description architecture, which finds the smallest hypersphere around normal samples, allowing for some outliers which might be present in the training data. We tested the proposed system on data collected from our farm and compared its performance to other one-class methods, with superior results. The performance of the system is highly dependent on the presence of occlusions, which represent a form of anomaly and anomaly type, and this is the subject of the future work. To illustrate the output from the system, here we've got an example where we train the system with the ripe fruit, and we can see this is what the system believes is the normal data, and these are the anomalies, and we can see that the performance is very high. When we extend our normal class to also unripe strawberries, we can see that there starts to appear examples which are not necessarily corresponding to the healthy fruit, and also some of the healthy strawberries are classified as anomalies. Finally, I'd like to present a couple of practical applications where these techniques can be applied to. So the first one is robotic harvesting, So this is an example where a combined 2D and 3D vision component detects and localizes strawberries, and then this information is used to drive the robotic arm to pick the strawberries. The second example is yield estimation, as illustrated in this BBC program called Country Files, targeting the countryside viewers, and demonstrates the use of the strawberry detection system for fruit counting, which can be used for forecasting yield. The presented selection of perception components demonstrates solution to practical problems in software production. There is many interesting academic challenges that are still left to address this problem properly. Occlusions is a big challenge, so here we are investigating techniques based on multiple views, multi-modal approaches, active vision, where we combine manipulation and sensing together. Another aspect is monitoring of other properties of fruit or plants, resulting in high throughput phenotyping information which can be used by the breeders, and also development of spatio-temporal models of fruit or plants whilst they grow for yield forecasting. I would like to thank you for your attention, and I'm happy to answer any questions. Here are my contact details. Thank you very much.